Welcome back. I'm going to do this simulation tutorial number 2, modal frequency analysis. It's a tuning fork. So this is a vibration analysis. Pretty cool stuff. So look at these dimensions here. So the overall dimension of the tuning fork is 120 millimeters, and then this 70 millimeters here is this length that we're going to end up playing with. So I'll move this off the side and get started on this. I've got Fusion up, and make sure you're on your preferences. I'm on Z up right here, and my so yeah, now we're going to go into simulation tuning fork A4. And we do need to save this, so I'll go Files, Save As, and Tuning Fork A4. I'll stick it in SimToots. Save it. Okay, let's check our units here. If we expand documents, we want millimeters, which is what we got, so that's good. Then we can jump straight into simulation here. And click this little, so click modal and modal frequencies, then click this little tiny little box right here, click that, change the number of modes to 12, and then go to mesh, click absolute size, we want 1.2 millimeters, back, create study, go to units. Very important that you change the units here to metric. So there's units in the original model, and then there's another unit setting in the simulation, and they can be different, but you do need to make sure that they're correct. And in this case, they're both millimeter. So click OK on that, and we're ready to solve. So I'll click this here. This pre-check says it's good. It's got a little green check which says it's good. They ask you to check the materials, study materials, and verify that it's stainless steel, which it is. Then go to this solve menu and click it. And I'm going to click run it locally and click solve. This little dialog comes up. Stretch this out a little bit. So I'll let that run, and I'll pause the video while that runs. Okay, it's done. So over here on this legend, there's these drop down with all these modes. So there's 12 modes. These correspond to degrees of freedom in the mathematical analysis, which is beyond the scope of this course. It gets pretty involved. But let's go to this results, tools, animate, turn that on, click this two-way button, crank the speed up to fastest, and click the play button and let it run like that. And then we can just look at these modes. Like mode 1, 2, and 3 are translation in X, Y, and Z. Okay, mode 4, 5, and 6 are rotation about X, Y, Z axes. And then 7, 8, and 9 are some other kind of XYZ thing, and 10, 11, 12 are another kind of XYZ thing. Most of these don't make any sense for this this particular object. Like mode 1 is showing translation from side to side in the X dimension, which makes no sense for a tuning fork. Now, if this were some kind of magnetically contained thing like a neutron or I guess a proton or an electron or something, and then maybe that would make sense, but it doesn't make sense for a tuning fork. And mode 2 is the translation in Y, which also doesn't make sense. Mode 3 is translation Z, which makes no physical sense for us. And mode 4 is rotation about the X-axis, and mode 5 is rotation about the Y-axis, and mode 6 is rotation about the Z-axis, none of which makes sense for this particular object. 7 makes sense. And that's the one we want. But the other ones are other kinds of wiggles and twists around different axes, and they wouldn't happen because you'd be holding the handle, which would dampen out the rotation there. Likewise, these other modes, aren't going to happen because you're going to hold the handle. The only mode that's really going to be sustained is this mode 7, because the handle is relatively still in that. All right, so if you look at this, it has a frequency of 470.9 hertz. Okay, we want 440 hertz because that's the standard in the world for for music. The middle keyboard on the middle A on a piano keyboard is 440 hertz. So we want to adjust the length of this thing, okay, to make it oscillate at 440 hertz in mode 7. So if we make it shorter, it will vibrate faster. So we'll cancel this animation, go to click finish results, and now there's this simplify mode. Okay, now simplify mode here in the simulation mode of this program, there's a simplify option which lets you make some changes, and these changes are not reflected back on the original model. So it lets you play with things until you get what you want, and then when you go back to the original model, it's the same. So here, and then there's this inspect. So let's click inspect and measure, and then click this edge, and you can see that's 70 millimeters from the tutorial first page, right? That's 70 millimeters. Okay, we want this to be let's see, it's vibrating at 470 hertz, which is too much. We want it to be faster, so we want it to be okay, wait, that's a little confusing. So it's 70 millimeters and it vibrates at 471. We want it to vibrate slower. We want it to be slower, so we make it longer. Okay, so we'll do a push-pull in the simplify mode. Okay, so go up to simplify, and click. So we're in this simplify mode in the simulation. So click this thing and this thing, right click, and press pull. And we want this thing to be longer now. So we type in 5 and click OK. Now we can go to inspect, measure, click this edge, it's 75. All right, close that. We'll finish the simplify thing, and we're still in the simulation mode, and then we can resolve with the new length. So we're resolving at a length of 75, and local, click solve. Okay, it's solving. This will take about a minute or so. I'll pause the video. And it's done. So we'll go to results, animate, just for fun. I mean, we don't really need to, but it's so fun. It's vibrating faster, but the thing we really care about is that it so now it's oscillating at 418 hertz with a length of 75, and it was oscillating at 471 at a length of 70. So we want to be in between that. And how far in between that do we want? Well, you can do a linear interpolation like this. And if you're interested in that, you can pause it and look at it, but I came up with 73. Now this is just solving for the equation of the line between those 2 points. This isn't exactly accurate because it's not a line, it's a curve, but 73 will get us closer. So we want this length to be 73. So I'll finish the results and we'll go back to simplify. And let's just check what we got. If you go to inspect, measure, click this edge, it's 75. But I want it to be 73. Now the weird thing about simplify is all the modifications are relative to the original distance. Alright, so if I want it to be 73, I gotta change it relative to the original 70. Okay, that is the 70 is the length in the base design. So I want it to be 73, but the base design is 70, so I want to do a push-pull of 3. So I click on this thing, got to hold down shift, right click, press pull, type in a 3, and you go OK, and then inspect, measure, click this edge. Okay, now it's 73, because I press pulled 3 from the original distance of 70, which is I find very irritating, but that's the way the simplify works. All the dimension changes are relative to the original base dimension, not the last simplify you did, but the original design dimension. All right, we close that, finish simplify, click this solve button, local solve. This comes up, cranks for a long time. I'll pause it, and it's done. And if you click this drop down here, it's 438. So our length of 73 gave it a 438, which is close to what we really want, a 430. All right, so I'll finish the result. So what they want you to do is go back to simplify and play around with this length in here of this edge until you get it to be exactly 440. Now that's going to take you a while, so I'll tell you the answer right now. We want a length of 72.81, and I just found that by trial and error. So let's see. So we go, we're in the simplify mode. I'm just going to do an inspect real quick. Measure. This edge is 73 right now, so I'm going to close that. Let's do a push pull. So I'll hold it, I'll click this, hold shift, click this, right click, press pull. I want it 2.81, and then I'll do an inspect, measure, 72.81, because I did a press pull of 2.81 relative to the original design dimension of 70. Okay, and that'll give me the frequency I want. Let's close that, finish to simplify, press solve, press solve again. This comes up, you let it run, I'll pause it, and it's done. That took about a minute in real time, and it's at 440. Bingo, that's what we want. Perfect. All right, and you can finish the results. You can go back to design and note that the original design has not changed. Like if now we're in design mode, if I go back to inspect and measure, click this this edge right here, it's 70. So you would have to do another press pull on the original design to get it to 72.81. All right, so this was modal vibration analysis. So a tuning fork is an obvious thing that you actually want to vibrate, but this is important for things that we don't want to vibrate, because everything has a resonant frequency. In this tuning fork, its resonant frequency is 440 hertz. But in real life, there's machinery that you often don't want to vibrate. So it's convenient or useful to solve for the resonant frequency and then check to see if you're stimulating the machine at that frequency anywhere. Like you might have a motor that's running at 400 at the resonant frequency, whatever that frequency is. Or you might have some other thing that's happening on the machine that if it happens to be at that resonant frequency, then that's bad. The whole machine will shake and you'll get vibration. So power tools, any kind of machinery you want to check for resonant frequencies and make sure that they're not, make sure that the machine is not resonant at the frequency that it's going to operate at, basically. Otherwise, it'll vibrate excessively. So it's pretty useful, pretty powerful stuff. All right, I hope this was useful to you. I'll see you next time.